Alrighty, so we got another PDA. Late at night while I'm recording this. What am I doing? Anyway, PDA. All right, for O to the N, 1 to the N. All right, so I'm gonna do. Let's do this one a more traditional approach. Let's actually use the dollar sign delimiter here. So how do we go about doing this? All right, obviously we got a start state. All right, our zeros and ones have to be the same. So let's have this. Let's call it state A. This is automatically going to be an accept state because at the start state we have 0 zeros and 0 ones. So that naturally works. All right. Next thing we need to do. Let's go ahead and set a delimiter for our stack. Let's set a delimiter for our stack. So that would be something along the lines of. All right. Now remember, like I just said earlier, we're going to have read. All right. And then we're going to have read pop. And then we push. So that is our format. All right. That's kind of our syntax that we need to use here. So we're going to read nothing. All right. We're going to pop nothing. We're going to push this on here. Okay. And this is going to signify, this dollar sign signifies the bottom of our stack. So right now, once we got past that, right, if we had a stack, it would look something like this. All right. We would have just added a dollar sign to the bottom of it. And that's important later on because we have to know when the stack is empty from removing that dollar sign. But we'll get there in a minute. All right. So we put a dollar sign on it. Next thing to do, we go to a state B. All right. Now, in state B, we need to read in all of our zeros. All right, we know that our zeros come first here. So let's go ahead and let's read those in. How are we going to do that? Let's put a loop on here, okay? And we are going to read our zero. We're going to pop nothing off the stack, all right? Because we basically just want to add our zeros to this stack, kind of up like this, right? We want to add those zeros. So we read a zero, we pop nothing, and then we're going to push zeros onto the stack, all right? So we can do that one time here. And we can do it again here. Yeah, I think this is right. Yeah. So we're going to do this repeatedly, all right? We're going to keep on reading all of our zeros onto the stack. Well, what happens when we hit a 1? What do we need to do when we hit a 1? All right, well, obviously we need to have a switch, all right? So that tells me there needs to be another state. All right, the state for us to read 1 is kind of like how we're reading zeros here. So what are we going to do? Let's make a state C down here to read those ones because right now they're not equal, all right? Right now we have a ton of zeros in the stack, but we don't have any ones. So what do we need to do? Okay. Well, once we read our first one, all right, we can take this path. All right. Once a 1 becomes available, we can read the 1. All right. And let's pop our 0 off. All right. And then let's push nothing on it. Let's push nothing on it. All right. Why are we going to do this? All right. So obviously when we have all these zeros up on the stack, we need to have an equal amount of ones. Well, how can we check that we're going to have an equal amount of ones? Well, if we pair every single 0 with a 1, all right, and just delete the 0 every single time we see the 1, then in theory, we should be left with what we started with down here with just this dollar sign. All right, that's what we should be left with. So what we need to do is we need to read the ones, pop the zeros, and we add nothing to the stack. All right, so once we see our first 1, we shoot down here to C. When we're in C, we just loop the process that we were just doing. All right. Reading 1s, popping zeros, pushing nothing. Okay? And that'll get us back down to with the stack. Every single time we see a 1, we get rid of a 0. Another 1, get rid of a 0. We'll eventually be left here. Well, the PDA, the way it works, all right, we have to have a DFA. We have to have an empty stack. Well, this stack still has, all right, this dollar sign in it. So how do we get rid of the dollar sign? Well, we just reverse what we did up here. All right, so after we've gotten rid of all the zeros, we haven't actually pushed any ones onto the stack, right? We've just been using it. We've reading the ones and popping zeros off, okay? So all this left is our dollar sign. So how do we get rid of that? We just reverse what we did up here. We'd say we don't read anything, all right? We pop off the dollar sign, and we don't add anything. We don't push anything back on. I don't know why I did that. We don't push anything back onto the stack, so it would look something like that. Okay, and that takes us to our D state, which is also an accepting state. All right, because at that point we know that we have an equal number, we've read an equal number of zeros and ones, and that would be what the finished PDA would look like. Pushdown automata. All right, so another example here for a PDA. All right, what are we going to do on this one? All right, so we have 3 variables, A, B, C, A to the I, B to the J, C to the K, where I, j and k all are part of a set of numbers where I plus k equals j. All right, so apparently we need to have like a, b, b, c. Like that would be a valid string. Like a, b, 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 c, c. All right, so where the i's plus the k's, so all of our a's and c's, whatever that amount is, that should be what our b's are. So we have 2 a's, 2 c's for 4, and then we have 4 b's. So it should look something like that. All right, so we need to have that as our final string result. So let's design that in a PDA, all right, using a DFA and a stack. And let's do it once more that unconventional way that doesn't start off the stack with a $sign or other delimiter symbol. So instead, let's just do it like this. So this will be our start right here, okay? So this will be our start variable. All right, now we know that the first thing, of course, is going to be the A's. We have to take care of the A's. We have to take care of IA's to be exact. So how do we do that? Let's just go ahead and let's read the A's into the stack. All right. So like I said before, all right, we're going read, then we're going to pop, and then we're going to push. All right, read, pop, and push. All right, so first thing we need to do, let's read it in. Let's read in our A's. All right, let's read in our A's. We don't want to pop anything because there's nothing on the stack technically at this time. So we're going to put our epsilon string symbol there, and then we're going to push the A's onto the stack. So if we had a stack, and we were putting things on it, it would just be looking like this as we just added A's to it over time. Okay, we're pushing A's onto, we're not popping anything off, we're reading in A's. Okay, so we get all of our A's, then check out this trick. We're going to use an epsilon transition. All right, if you remember these from DFAs, these things are really cool. It basically just means you don't have to do squat, which I love. So epsilon transition to the next stage. So once you've written all the A's that you see, and you hit another, if you hit another variable, hit another thing, just boom, pop down into this, pop down into this. All right, so what are we going to do in the second one? We have two options, all right? We know that our B's are technically, half of our B's are going to be all of our A's. So the number of A's, the total number of A's should be half the number of our B's, all right? Because I plus K equals J. So how do we go about doing that? Well, you need to do two things here, I think. First, when we see a B, we can state this state. When we read a B, all right, let's pop an A off. And then let's not add anything to the stack. All right, so I see a B coming in. I'm just going to knock off an A. Boop. I see another B. I knock off an A. All the way until all of my A's are gone. All right, so when all of my A's are gone, in theory, I still have more B's, all right? Because if I had 3 A's, then technically, for the right string, I would have like 6 B's, all right? Because the rest of these would go with C's, technically. So, okay, I read this B, I get rid of this A. Doop, doop. I read this B, I get rid of this A. And I got the stack empty, but I still have all these B's that have to be read in. What do I need to do with those? Oh, okay, well, simple. Let me just add another loop here. And let me just say, I read the B, all right? I don't pop anything at all. I push the B onto there. Okay, why are you going to do that, Sam? Why are you going to do that? All right, well, I have all these B's, so just because I can maybe do the same thing again with C's in a second, all right, and have that empty stack. So for all these B's that are left over, what if I just added them back onto the stack? All right, what if I did that? What would end up happening? Let me rewrite this stack. This is aggravating me. All right, so I got the stack. I have A. All right, I read a B, get rid of an A, read a B, get rid of an A, read a B, get rid of an A. All right, and then I still have another B. Well, because this is deterministic, it can choose which path it wants to do. Well, it can't get rid of it. It can't pop off any more A's because no A's are in the stack. So instead, it has to go to this, whatever this is, which says that I don't need to pop anything. I just need to add a B. All right, so I'm going to add a B. I'm going to add a B. I'm going to add a B. And it would look something like that. All right, what's the next step? What's the next step? Well, let's do another epsilon transition. All right, because once we've added all the B's we can add, we're going to come in contact with a C. What do we need to do? Well, we're going to hop down to this last state. All right, well, let's call this our accept state. This will be our accept state. And I'm not going to be able to fit that word in there, but you get the point. right here we have a loop, and we basically just copy what we did up here, kind of, sort of, except for this time. All right, we see a C. Let's pop a B off, and let's put nothing back onto the stack. All right, C or B, pop nothing. Read a C, pop a B, put nothing on the stack. All right, so then we have this up here. We have those C's coming in, and C a C, pop it off. C a C, pop it off. C a C, pop it off. And just like that, we can get rid of all of our C's. All right, we can get rid of the rest of our B's, and they should match up with the amount of C's that we have left over. All right, and if we do all that and the stack comes out empty, we're already pointing an except state, and therefore this is valid. All right, so let's test this. So let's say we have A, B, 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 C, C. All right, how would this look? All right, so let's say we're reading A's. So we read in an A, read in an A. All right. Oh, we come in contact with a B. What do we need to do? Epsilon transition down here. All right. Read a B. Let's pop an A. Read a B. Let's pop another A. All right. Oh, we still got two more B's. So let's read a B. Pop nothing. Add the B back. All right. Do that again. All right. So we read our two B's. Oh, we come in contact with a C. What do we need to do? Epsilon transition down, because you can't do it. You can't handle C's here. Epsilon transition. All right, and then we come down here, we read a C, we pop a B, don't add anything else. All right, so we pop a B, read another C, pop a B. All right, empty stack, we're pointing an except state, therefore this is valid. All right, let's do a string that isn't valid. What would that look like? What would a string that's not valid look like? All right, let's do A, B, 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 C. Yeah, that's a not valid string. All right, how would this work? All right, let's read in our A. So we have an A, see that? So boom, A. Okay, we have another A, push it on, another A, push it on. All right, oh, we come in contact with a B, epsilon transition down to our next state. This state handles all of our B's. All right, so we have an A on the stack, so let's get rid of it. So 3 B's, 3 A's, B, boom. Another B gets rid of another A, another B gets rid of another A. All right, and we have an empty stack again. Okay, now we go to C. What do we have? Oh, we see C. Read a C, pop a B. We can't do that. There's no B's left. There's no B's left to pop. Therefore, this can't complete. So we can't do this. So it just doesn't work. You can't execute that. You can't pop something off a stack that's not there. Therefore, this epsilon transition is basically stuck somewhere in here. All right, stuck somewhere in here, because you can't get to this last loop. Therefore, you never hit your except state. Therefore, this is negative. All right, and that is how you do a PDA for A to the I, B to the J, C to the K, where I plus K equals J. Alrighty, so here is what we need to create a PDA for. All right, so we have a string W that's made of the alphabet zeros and ones, any combination of those as many times at once, where W, or omega, I guess I should say, has the same number of ones and zeros. Okay, so how do we create a pushdown automata? Yeah, how do we create one of those for this? All right, we can do this for one state actually. And this is gonna be kind of crazy, so just like stick with me. We'll see what happens here. So we have a state, right? Okay, this is going to be our except state. Now keep in mind, we remember, right? You have with a PDA, you have a DFA, and then you have a stack, and both have to be checked off for the PDA to be true. All right. So even if we have it going to the except state here on this DFA, but the stack's not empty, then we know that the DFA is not valid. All right. So how do we do this? Well, we have to have the same numbers of zeros and ones. Let's see. First thing, let's read in our zeros. All right. So we're going to do a loop here, and let's say, so remember, it is read, and then it is pop, and then it's push. That is that's kind of the format we need here. So let's say if we come in contact with 0, we read the 0. Okay. That means we pop nothing. All right, because assuming there's nothing on there, so we read the 0, we pop nothing, and then we push the 0 onto the stack. All right, and we can do the same thing with the 1. We can do the same thing with the 1. So we can go, if we read a 1, we push nothing on there, and we take that 1 and put it on the stack. All right, so what do we do here? We can also we read the 0, we pop 1, all right, because we have to have the same amounts of 1 and 0. So in theory, if we read the 0 and we pop 1, all right, and we push nothing, that'll clear all the 1s out the stack that match with the 0s. And following that same logic, we can do the same thing over here. We can read the 1s, pop the 0s, and push nothing. All right, so this right here technically is a complete PDA for omega has the same number of 1s and 0s. Because if we have a string, let's say 0, 0, 1, 1, okay? Well, how would the stack look? How would the stack look? So we start, we read a 0, we have nothing, and we push a 0 onto our stack, okay? We read another 0, we put it onto the stack. All right, and then we come in contact with this 1. Well, what do we do with a 1? Well, the computer can choose automatically because, you know, it is deterministic. The computer can choose to read the 0, read the 1 that we see here. Okay, we read the 1, we pop the 0, all right, and we don't do anything else. So, or we can add the 1s on top. It really, yeah, it reads the 0, pop the 1. All right, so that deletes that one. So it reads the 1, pops the 0. My bad. There we go. Reads the 1, pops the 0, pushes nothing onto the stack, getting rid of the 0. Okay, we do it again. We have another 1. We read the 1, pop the 0, push nothing. Leaves our stack empty, and we're pointing at an accept state here. So this, of course, is the accept state. Just like that. So thus we know that this works. Now let's try something that doesn't work. So what's the test case that doesn't work? That would be 1, 1, 0, 1. Something like that. All right, we're the same. We don't have the same number of 1s and 0s. How would this work? All right, so we see a 1. So we're going to read a 1. We're going to pop nothing. We're going to push 1. All right, that's what the computer chooses to do. It does the same thing again. All right. Then we get to the 0 here, and it says, what can we do? Well, we can choose to read the 0, pop nothing, and push the 0 on, or we can read the 0, pop a 1, and push nothing on. So let's read the 0, pop a 1, put nothing back on it. All right, and then we left with one more 1. We can read the 1, pop a 0. Can't do that. There's no 0 here. We can read the 1, do nothing, and add a 1. Yep, that's the only option we can do. All right, and it puts this back on, and it's pointed at the accept state. But because the stack is not empty, then we know that this is a fat no here. So this doesn't work, but this does. So hopefully that's just a great quick example of how these how pushdown automata work, and in kind of an easy way. A lot of people, they like using you know, I think it's a dollar sign. It's like a delimiter or something. I don't do that. I just don't find that easiest, but that is an option if you choose. This method doesn't work for you, but I like this. It's simplistic, and it always works. So thanks for watching.